Dr. Fairline first?
Everything.
Okay, now we come to a couple of questions on the temperature scale, and it says what temperature is there for which one? Okay, now we're going to do the demonstration of thermal expansion.
That's some of the good ones. The one that I want to show you okay, at least here.
Back. Now I'm going to illustrate how one can, using the ideal gas law, how one can do a simple experiment and demonstration to calculate the temperature of absolute zero. How many Celsius is absolute zero equal to? So I have this pressure gauge here. Basically, the pressure gauge is a ball here, and the ball is able to tell the pressure on it, and the gauge is connected to this gauge here. And so right now it's showing about 15. That's atmospheric pressure. To be more exact, it's 14.7. Atmospheric pressure is 14.7 psi, pounds per square inch. But on this reading here, it's not really a very good digital scale, but I can tell that it's about 15. So the temperature right now at room temperature, I can make this one data point. At room temperature, what the pressure is, that's about 15 psi, right? Okay, you can see now I have the computer open and I'm going to make an Excel file. The temperature in the room is 24.4 Celsius, 24.4, and then we saw that the pressure was 15. 24.4 Celsius, right? Water bath right here.
So the idea is to take this fact that pressure, in that case, the volume of the bowl is constant, right? So this one is held constant, the number of moles is held constant, so pressure should be linear function of temperature. So we have the ball's volume. We don't really even need to calculate the ball's volume. We just need to establish a linear relationship between the two. So when the temperature is at, what was the temperature? 22 Celsius? Yeah, 24.4. So 24.4. And then the pressure was, we can put 15. So that there's one data. So I need at least 3 data to make a straight line. 2 is not good because any 2 lines, any 2 dots will make a straight line. All right, so I need at least 3 data. So then what I'm gonna do is I'm gonna take that ball, insert it in a cold bath and maybe a hot bath, and then read the pressure. So 2 other data.
The temperature there is 0.1 Celsius, right?
That's a
0.1
cold
Celsius. You can see here.
So there the beaker down
It's
here.
going to be 0.1 Celsius.
Right here.
And then I'm going to put my pressure gauge in there, determine the pressure. So it should go way down, right? All the way in. And the pressure should go down. Do your best to try to read this 11, 12. Again, it's not a digital scale, so 11, 12, 13, 13.5. 13.8 is my best guess. 13.8 psi. Okay? Okay,
So that
then I'll
one is
measure the temperature of my
0.1 Celsius.
Okay? So the temperature is going to go way, way up. It's going to be 73.0. 73.0 Celsius. But of course, it's going to drop quickly, so I should do this quickly. So it's going to be 72 point, right now, 72.6. Okay, and then immediately determine the pressure. So the pressure should go up.
So the pressure goes
Up,
up.
up, 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 up. So what I'm going to do, at the instant that I record the pressure, I'm also going to record the temperature. Okay? So it's going to be right there. There's going to be 15, 16, 17. The pressure is 17.2. And the temperature is 71.9. 17.2, 71.9.
Now, ideally, you could get maybe 5, 6, 7, 8 data points, different baths.
Okay, and then we have a 71.9 Celsius. So you got 3 data points right here. Okay, so what I can do is I can put here the temperature at the left. Right.
So then I'm gonna go put this on
On a
Excel.
scale 0 Kelvin, right? The pressure should be 0. So the 0 Kelvin is defined as the temperature where all molecular motion stops, and at 0 Kelvin, right, which is absolute 0, the pressure in the pressure gauge should be 0. Molecular motion stops, and therefore they stop hitting the walls of the container, and they have no more pressure, right? So 0 Kelvin is also analogous to the gas having no pressure, right? So then I'm going to make a plot of this. Then I'm going to go insert. Then I'm going to go scatter plot. Right? And then the 3 data points I have should be approximately linear
Looks like
line.
a pretty good straight line.
Of course, since I did it in Celsius scale, these 3 are going to give me a linear line, and then this is going to keep going back, keep going back. How far back is it going to go? Well, it's going to go all the way to negative something, 200, 300, 400, whatever.
Right.
At that negative something temperature, right,
Keep going.
the pressure is going to drop to 0, you see. So if we had no clue what absolute 0 is in terms of Celsius, we could do this little experiment to determine that. You need at least 3 data points to do a good fit. If you just had 2 data points, it wouldn't be a good fit because any 2 data points would create a straight line, right? So then I'm going to go to Excel and I'm going to say, give me the trend line. Then I'm going to say linear line. Right, and then I'm going to say trend line. This detail here. Make this bigger. So of course the Y means pressure. And T means temperature. X means temperature, right? So I can change my data points. This is pressure, this is temperature, but the temperature is in Celsius, right? So of course this is an increasing function. Then it keeps going back. The R-squared value is pretty good. R-squared equals 1 would mean all the 3 points perfectly fit on a straight line. That means I don't have any deviations. Actually, my data is actually good. 0.9997 is approximately 1. That means
Not bad, huh? So I proved pressure is proportional to temperature. Which one was that called? Charles's law?
I might have systematic.
I forget
error
which
in my
one is
lab
called
because I
which
can't
one.
beat because this is not a digital scale. I can't beat
well,
the scale.
probably doesn't matter.
So I might
You
have
don't-
systematic.
you don't need
error.
to know the
Instrument
name of it.
might be flawed a little bit, but I don't have too much random error. That means the three points line up in a straight line. So here's my equation then. Okay. Pressure is equal to 0.0472 T plus 13.816. Okay. So now let's set the pressure equal to 0, right? Because as this line goes back, at some point the pressure is going to be 0, right? Pressure is going to be 0. So for what temperature? What temperature in the Celsius scale causes the pressure to be 0, right? So then what's that going to be? Then you're just going to take this to over there, negative 13 divided by this, right? That means at that Celsius temperature, pressure will drop 0. That means this is equal to 0 Kelvin, right? 0 Kelvin. How is my result? Well, people that have done this experiment over and over much more accurately tell us that negative 273.15 Celsius is 0 Kelvin. Absolute 0 is equivalent to negative 273.15. I'm pretty close. I'm within 20 Celsius of that.
What was the answer come up?
We're using a crude experiment like this with reading without having it.
Where was that online calculator? So it was 13.816. Not bad, huh? This is the type of experiment that's simple enough. You can have middle schoolers, right? Prove the ideal gas law. You're not only proving the ideal gas law, it's a simple experiment, but you're actually calculating the temperature of absolute zero. There's another one you can do with the keeping the temperature constant by changing the volume, right? That one is called, there's Boyle's law, there's Charles's law, and there's Guy-Lussac law. And I always forget which one is which. So I think this one.
Okay, welcome back. Now I'm going to do a demonstration. I'm calling it Charles's law and absolute zero temperature. So it's going to be similar to the video that I did, the demonstration on Boyle's law, where I graphed pressure versus 1 over the volume, and I showed that it's a straight line. In Charles's law, we're going to work on the relationship between volume and temperature of a gas. So we have PV equals nRT, where the pressure of a gas is constant, right? And volume is linearly proportional to temperature. So that is what I'm going to
Well, I'm keeping
volume
pressure
is
constant
proportional
now.
to temperature.
Volume is proportional
So I'm
to
going to be
temperature.
getting 3 data points from this, for volume as a function of temperature. One of the things that I want to show is that this gives you a straight line. It should be giving you a straight line there. The other way that I can use this demonstration is I can actually predict what the temperature of absolute zero is. This is, I'm going to be plotting it as a function of Celsius. So this is 0 Celsius. So then I can extrapolate back and I can find out what temperature we must reach so that the volume of the gas reaches 0. So when we reach absolute 0 Kelvin, right? The gas should contract, and it should eventually have no volume at all. So that point where it has no volume is the absolute zero temperature. So we can extrapolate the graph backwards, and we can see what the temperature of the absolute zero is. I've done a couple other demonstration videos that you guys can watch. One is the Boyle's law. In Boyle's law, we were concentrating PV is a constant, right? So we said that
Now that's going to answer us which one is which. Boyle's law is the pressure
1 over the volume,
is
but I
inversely
was
proportional
doing
to
only
volume.
the height because the area, surface area of the tube wasn't changing. So I graphed 1 over the height. Then I showed that this gives you a straight line. I got several data points, and I showed what kind of straight line gives you, how close to a straight line that gives you. The other video that I've done is also similar to this, where I took a pressure gauge and I put it into different containers of water, and I found the pressure. So there I was concentrating on the relationship between pressure and temperature. So one is pressure and volume, the other one is volume and temperature, and then the third one is pressure and temperature, right? PV equals nRT, the relationship with pressure with temperature. So in that demonstration, I graphed P versus T, and I got 3 data points. Then I proved that those points give me a straight line, and then I extrapolated it backward, and I got the temperature for absolute zero. So it ended up being a very good result to what it's expected to be. So let's see how this lab goes. So the way that this is going to work is I have a test tube here. It's 50 milliliters is the volume of the test tube. So I put a stopper on it, and it's getting warmed up in water. So what's going to happen to the air inside of that test tube? It's going to start expanding because the water is heating up the test tube and the test tube air. The air expands and it leaves the test tube, right, through the opening here. The opening is open, so the air expands. After the water starts to boil or reaches near boiling, I can take out the test tube and I can put it into different water baths, right? One, I have a water bath here in the middle. I can find out what the temperature of that is, right? So the temperature of this one, the middle one, 28.0 Celsius. 28.0 Celsius. So what's going to happen? When I take the tube and I'm going to put my thumb over it, over the top, right? I'm going to put my thumb, I'm going to close it, then I'm going to take it and insert it into the water, then I'm going to release my thumb, right? When I release my thumb, what happens? The air inside of the test tube decreases in volume, right? Why? Because it gets cold. When I release my thumb, because the air contracts, the amount by which it contracts, water gets into the test tube, and a small amount of water gets in there due to the contraction of the air. So then I lift that up and I measure how much water got in there. That tells me how much is the final volume of the air. I subtract 50 milliliters, which is the original volume of the air in the test tube. That's the original volume. Then I subtract from there the amount of water that got in there, right?
Clever,
and then
huh?
I find out the final.
This guy's pretty clever, man. So what's in the test tube originally? Nothing, just air. I'm heating it up so that the number of moles, I can control the number of moles of air. And since it's open, the number of moles is gonna leave to keep the volume 50, right? And I'm gonna put my thumb over it, go and then put it in a colder bath. The air shrinks, then release the thumb, the water gets in. Right, and then I can calculate how much water got in, and that's gonna be the final volume of the air.
I put the test tube back into the container of boiling water, right? I let it heat up again. Then I do the same thing. Take it, put my thumb over it, put it in the bath of ice water. So the temperature of the ice water, okay, the temperature of the ice water is 2.0 Celsius, 2 Celsius. Okay, now the water is at the boiling temperature. I'm going to measure its temperature right here. It's 97.5. At this point, I'm going to take the test tube out. 97.5 was the temperature of the water. You want to close the thumb right here.
This one's a bit harder to do.
Put the test tube completely, immerse it in the water, right? Then let go of your thumb. A little bit of water will get inside of the test tube. Okay? So you can see here, the test tube has a little bit of water in there. Okay, because the air inside of the test tube shrunk, contracted, right? And so that space was filled up with water. So let's determine how much water that is. 5, 5.5, 6, 6.5, 7, 7.5. Okay, that's about right there between 7 and 8, 7.5 millimeters. Okay, so then the original volume of the air in the 97.5, the volume of the air is 50 milliliters, right? When I put it into the temperature, the regular room temperature water, right? How much 7.5 milliliters of water came in there, right? So that means the volume of the air, the final volume of the air is 50 minus 7.5. So 50 minus 7.5, and you get 42.5 milliliters of water. Let's retest the temperature of that water. I get 26.3 Celsius. 26.3 Celsius. Okay, so we can change that over here. 26.3 Celsius. Okay, now let's put the test tube back in. Close the stopper.
Okay, let's go over this.
Fifteen and a half, 16, 16 and a half, tube back in.
So now I heated it. I put it in the cold one. The cold one, it shrinks more. Oh, you see, you can tell a lot more water.
Okay, so now more water got in there, right? Because the air contracted more. So you can see here the level of the water.
Okay, then measure it.
In the volume of the air. Okay, now we can do a plot of volume versus temperature. On the left side, we can put the temperature. On the right side, we can put the volume. The lowest temperature will be 3.6 Celsius, right? The volume of the air will be 33 milliliters, right? The next temperature will be 26.3 Celsius, and the volume of the air will be 42.5, right? Because 50 minus 7.5. And then the original temperature of the water is 97.5, and then the volume of the air is 50 milliliters, right? So let's do that plot on Excel, and let's see what. So you can see it's not a perfect straight line. So let's get the error from that.
This one wasn't as good of a straight line.
So I'm going to ask for the display equation on the chart, display the R squared value. Okay, so the equation is going to be, let's make the font bigger here. Here, this is the volume. So one of the things we wanted to show, volume is linearly proportional to temperature, right? R squared value 0.8775. So it's about 12.5% error, 12.25% error, right? So if this one was 1, that would mean perfect straight line. That would mean it is a perfect straight line and the fit is excellent, right? So we're not getting that good of a result. So you can say 0.8775, about 12.25%. And then this is the equation that we're getting. So for the volume. So let's put that down and then do our calculation on that. Okay. Now if I put the same data into Logger Pro, let's see what Logger Pro gives me.
Okay, so
it might give me slightly 29T plus 34.916. So calculate what temperature would cause the volume of that air to go down to 0. And then that's going to be the temperature of absolute 0. So then you're going to have Celsius. That one I'm not really close to because we know that the temperature of absolute 0 is going to be negative 273.15, right? So if I was doing an experiment, I would repeat this and I would see, okay, which one of my readings is off? Repeat this. Or the best way to do it is do this at multiple temperatures. Find the temperature of the air at multiple different temperatures. Like if I have a...
Yeah, so this one wasn't as good of a result, but you get the idea that you're still proving that the volume is linearly proportional to temperature. And then if we had different heat baths, you could do more because the way that the data looked was sort of like this. So one of these dots throws it off, but if I do another dot, then you get a much better accuracy, you know. And then whichever one is the odd man out has less of an effect. And then you can redo that and get a better answer. Okay, so cool. That's a good connection between the ideal gas law, proving the ideal gas law, and also doing some experiment with the temperature scale.